Then comes the quality control, a very important step to have a sound joint. We have 3 modules for that. In module 19, we will discuss tests related to adherent, adhesive, and manufacturing process. So we have seen the manufacture part. It's time to talk about quality control. And we will start with adhesive, adherent, and the manufacturing process. Concerning the adhesive, one property that we often verify is the viscosity, because it has a big impact on the wettability and on the degradation of the adhesive. The shelf life is controlled basically by the viscosity. Another property that is related to viscosity is thixotropy and thixotropic materials. Some adhesives in the paste form are thixotropic. What is this property? Well, if you mix the adhesive, it will flow easily and will not offer a lot of resistance. However, if you don't touch the adhesive and you put on the wall, for example, it will not sag, it will stay in place. That's what a thixotropic material is. So very, very useful for paste adhesives that need to fill gaps, sometimes up to 10 millimeters. You have here some viscosity values, and you have an epoxy, a typical epoxy paste, how it compares with other materials that you know. Another property that is generally controlled is the TG, the glass transition temperature. This is a key point because a structural adhesive is only structural if it is used below TG. Fortunately, there are many ways to measure the TG. Every property will have a big change at TG. It can be the heat capacity, modulus, hardness, dimension, volume, etc. At TG, a huge change in the property. But probably the test that is most commonly used to measure TG is the dynamic mechanical analysis test, DMA. So in that test, you use the specimen, you want to measure the TG, and you apply a sinusoidal stress wave, and you measure the strain response. And then you increase the temperature, and what happens is that when you are at TG, the phase difference between the two will be maximum, because there is maximum damping, there is maximum viscoelastic behavior of the adhesive, which is exactly represented here, where you have the property versus temperature, and tan delta is that phase difference between the two related to damping. So one very good way to measure TG is measure the damping of the material, maximum damping at TG. There is a machine that we use that was initially developed at Bristol with Professor Adams, which is the constraint layer at resonance. It's basically the DMA, but a bit faster. We use this type of specimen. It's an aluminum beam, you see. The adhesive is here between the aluminum beam and a top metallic plate. There are some magnets at the end because this will go into some coils that will make this vibrating. It will have this shape and this shape. There is here a string corresponding to the node, and this is put at resonance, okay? Then we put this into an oven, very small oven, and we increase the temperature. And there is a feedback unit, as represented here, that maintains this at resonance. And because the chamber is very small, the heating will be very quick. And if you measure during the test the temperature and this maximum displacement of the beam, when the displacement is minimum, that means maximum damping, you can measure the TG of the adhesive. The beauty of this method is that it's very, very fast. In 1 minute, you have the result. That means you don't change the state of the adhesive. For example, imagine you want to assess the effect of water. This will not dry the adhesive. Or imagine you want to assess the TG of a partially cured adhesive. This will not also affect the state of the adhesive. There is a link here that we can open where we have a full description of this apparatus. I'll let you read this in more detail if you are interested.
I'm going to talk about this machine that we have that is called glass transition temperature measurement device. This machine is used to determine the glass transition temperature of polymers, such as the adhesives that you see here. So how does this machine work? We have this specimen, which is a beam, and this beam has adhesive inside this constrained layer that you can see here. So there is a metal sheet. The adhesive is located here between the layer and the beam, and it's fixed in position by a screw. Then this beam has two magnets on each side. These magnets are going to be driven by these coils that you see here, and they will impose a vibrational movement to the specimen. So the specimen will flex down and up, down and up. And this will load and unload the adhesive layer. To determine the glass transition temperature, what we need to do is use this oven to increase the temperature gradually until we reach a point where the specimen damping is maximum. This means that the adhesive has reached the glass transition temperature. And during this transition, it becomes very capable of absorbing these vibrational movements. And this will be reflected into a peak of damping. So we will insert the specimen within our testing machine, and we will start the software that will put the specimen in resonance, increase the temperature of the oven, and then detect the glass transition temperature.
Let's go back to the quality control, and let's talk about adherent. I will not go through all the tests that exist to characterize the adherent. Doesn't make sense. That's not the purpose here. But I will discuss in particular one property that is extremely relevant in the world of adhesive joints, which is the transverse strength of composite materials. You know that composites and adhesives are married, but we can have the problem of delamination. So we really need to know the strength through the thickness of the adherent. One way to do it is simply to bond the composite to metallic blocks and then pull the composite specimen. You might have problems of stress concentration. It might not break exactly in the composite, and there are ways to reduce the stress at the edges in the composite and make sure it falls right in the composite. But this is a property really that you should know. Then, still about the adherent, of course, the surface energy, that's an important parameter. There are some simple tests, such as the water break test. Very easy. You simply spray water at the surface. If the water forms drops like that, it's a bad sign. If it forms a uniform film, that's very good. But that's not a quantitative test, just qualitative. You can use Dyne pens, that works very well, and it gives a very, very fast answer. So you have pens of different surface energy, and you paint your surface. If the ink can wet properly the surface, that means the surface energy of your substrate is higher than that of the pen, for example, higher than 30. With 44, we have a problem, it doesn't wet properly. So the substrate, the surface energy is between 30 and 44. Like this, you can have quickly an estimate of the surface energy. But if you want a rigorous measurement of the surface energy, then you need to go for the contact angle measurement. We need at least two liquids of known surface energy, and you are going to measure the contact angle of these two liquids. If you have more, better. And this is related to the Young equation that we have seen in the theory of adhesion. If you take again that equation and you express the surface energy in two components, the polar and the dispersive, then you are left with one equation with two unknowns. which is the polar and the dispersive component. That's why, to solve this equation, you need to measure the contact angle of at least two liquids, so that you have two equations for two unknowns. That's how it's done in practice. In general, we use more than two, we use at least three liquids. Again, more about adherent properties. Surface roughness. We know that the surface roughness has also an influence on the joint strength. This is related to the theory of adhesion, the mechanical theory of adhesion, the effect of interlocking. So it's important also to assess what's the roughness of the adherent if we want to relate it to the final results of the joint strength. Of course, again, this you know as well as me, the various methods that exist. The profile instrument is the most common one. You do a line and you have an idea of the surface of the substrate. However, many times the stylus gets used and you might have wrong results. So if you want to use something more precise, you can use laser or AFM, atomic force microscopy. This is a bit the same principle as the profile instrument, but the stylus is really very, very, very tiny, so you have a much better precise idea of the surface, and it's a scan, so it's an area that you have at the end. Okay, about the manufacturing process, as you can see, there are many things that you should control. All are more or less obvious. You should use your eyes, the consistency, viscosity of the adhesive, air entrapment, be careful with the shelf life, the laboratory clean, temperature, humidity, control very well the adhesive thickness, and the curing process. Everything more or less straightforward. About the curing, you should be really careful about the temperature and make sure you have a thermocouple next to the adhesive and only count the time of curing from the moment the adhesive reaches the cure temperature. To understand how the adhesive cures, what's the degree of cure as a function of temperature at time, there are many ways you can do this. One common way is use DSC, differential scanning calorimetry. You measure the heat flow through the specimen, and that heat flow as a function of temperature will change as the temperature gradually cures. Another way is to use the EMA that we have already discussed before, the damping, the storage modulus, etc. These properties, they will change also as the adhesive cures. And finally, another test that is very commonly used to measure the degree of cure, and not only that, the chemical composition in general of the adhesive is FTIR, the Fourier transform infrared spectroscopy. So you use infrared light to scan the sample and measure the chemical composition. And this, of course, will change with the degree of cure or with the aging of the adhesive. So that's for the first part of the quality control.